All right, we're going to be looking at our second video in 11.1, talking about derivatives yet. Just going to revisit an example that we did in the last video, the last example that we did right here, where we found the derivative of f at 4 of the function 2x squared minus 3. Just wanted to point out that if you would like to, another way to kind of handle this is to find these two things, f of 4 plus h and f of 4, uh, like outside of this whole problem here, and then kind of stick those things back in. It might be a little bit cleaner way to do it. So we kind of did that with the f of 4. I did that right here, and then I put the 29 in. But you could do the same thing with the f of 4 plus h. You know that this f of 4 plus h means that you're going to be putting 4 plus h into the x value in our function. So that's what it's going to look like. And then you can FOIL this out and come up with the 2h squared plus 16h plus 29. You know, once you simplify that whole thing, and then you could put that in the first step of your limit. It just might save some of these steps in writing. You know, I guess what you're really saving is writing a limit that many times, because you're going to put it right in, and then only have to simplify maybe 2 or 3 more steps after that. Just a suggestion. All right, let's take a look at this first example here. In this video that we're going to do is finding instantaneous velocity at the indicated value of t here. So we have s of t is 4t minus 3, and t is 3. So when we're asked to find the instantaneous velocity at a t value of 3 in this function, what we're looking for is s prime of 3. We're looking for the derivative at 3. So let's find that here. All right, so let's find s prime of 3. I'm going to again use the limit definition of a derivative where h approaches 0. Okay, so we want our change in our x values to be h, the denominator is h, and we're going to have f of, well, sorry, I only mess that up every once in a while. We want s of t, oh no, we're putting 3 in here. S of 3 plus h and s of 3 are going to be our two y values. So what I'm going to do is kind of what I talked about in that last problem, or at the beginning of this video here, is I'm going to put 3 plus h in for t, and I'm going to put 3 in for t. So let's do the easy one first. S of 3 is going to be found by taking 4 times 3 minus 3, which is 9. And s of 3 plus h, I'm just going to flip that h plus 3 around, h and 3 around. It's going to be 4 times h plus 3 minus 3. And that's going to give us 4h plus 12 minus 3, which is 4h plus 9. So now that I've done these two things already, my next step, I would say that's about as much as I'd want you to do before you put it in. You know, you probably see what's going to happen with the 9s already, which is awesome. But let's just hold off on that until we can actually see it in play here. So we've got those two expressions on, and now we can say, hey, these 9s cancel out, and we're left with the limit as h approaches 0 of 4h over h, and all those h's cancel out, and And we're left with the limit as h approaches 0 of just 4. Now, it's been a while since we did some of our limit problems back in the prerequisite chapter back in first semester. So one of the things you need to remember is that the limit of a constant is the value of the constant itself. So I'm just going to put that as a little reminder here. The limit as x approaches a of some constant c is just going to equal c. So basically what we're saying is, okay, let h approach 0. Well, there's no h to put 0 in for, so this is just going to equal 4. So we have that s prime of 3 equals 4. The derivative at 3 in the original function is 4. The slope of the tangent line at 3 is 4. And the instantaneous velocity, which is what they were asking us for, is 4 feet per second. All right, what I'd like you to do is take a look at that function, the original function. 4t minus 3 is a line. It's a line with a slope of 4. So guess what? We kind of knew from the very beginning that our slope was going to be 4. It didn't even matter what that value was. Our answer, no matter what, would have given us a value of 4 at the end, because that tangent line at any point would just be the slope at that point, which is always going to be 4 for this function. So basically, the derivative of a linear function is the slope of that linear function. All right, the last piece of this section is now kind of putting this all together and finding the derivative of a function. Okay, so instead of just finding a derivative at a point of a function f, we're going to find a whole new function that represents the derivative of the original function. So as we're doing this, we're going to illustrate a few new notations. We can have f prime of x like we've been using. We can have dy over dx, which is called Leibniz notation, and it means the derivative of y with respect to x. Basically, you're naming your dependent and independent variables here. The notation has both variables in it, which can be useful in some cases that we're doing. These are going to be the only two notations you see in our book. There are more, but these are the two that you're going to see as you're going through our pre-calculus problems. And they both mean the same thing. If you're asked to find dy dx, you're being asked to find the derivative of y, or the function. So I'm going to write that f prime of x, the derivative of some function f, which is also written as dy dx. Actually, one more notation that you might see, so I'm going to put it down here, is d dx of f. Or of f of x. Okay, all of these things mean find the derivative of the original function f. So we have the limit as h approaches 0 again. Same idea as before. We're looking for the change in the x values to become 0. The y values now, instead of f of a plus h, we're not putting in a value for a. We're leaving it as x, but we still want that difference in the x values to be h. So one of my x values is x, the other x value is x plus h. We're looking for h to approach 0, so that would go away, and this would become 0, and we'd be basically taking y minus y, where y's are the same value. X minus x is represented by h, and that becomes 0. So you're looking for instantaneous velocity just like we were before. It's just that now we're not putting a value for x in called a, it's just finding the derivative of the function. As long as that derivative, excuse me, as long as that limit exists, it's differentiable, uh, and we can find the derivative. Okay, so let's try this out with a function f of x equals x squared. Okay, familiar function. We've actually dealt with this function a couple times in this section already. So we're going to find f prime of x by taking the limit as x approaches, as h approaches 0. Actually, I'm going to do this here. And we're looking for these two y values here. F of x plus h. Actually, all I'm doing right now is rewriting the formula from up above. And here, f of x. So what we're going to do is, I'm going to find these two things kind of, I'm going to do f of x first here. I'm just going to write some notes over here. F of x, we already know is x squared. I mean, really, it's right there. I just rewrote it again in blue to match colors that I have in my problem that I'm setting up here. So we already know that this is going to become x squared right here. H is h. All right, so the f of x plus h means put x plus h in for x. So I put x plus h in for x right there. Now we need to find what x plus h quantity squared is. If you remember our binomials, our square of a binomial pattern, that's what we get right there. The faster you know that pattern, the better, because we're gonna be doing a lot of foiling out. Uh, Binomial expansion, very useful. You know, where we'd have something like this, a plus b to the n, and we use Pascal's triangle, the numbers from Pascal's triangle to help us expand that out. Those sorts of things become very, very useful in calculating these derivatives. All right, so here's where we're at. Taking the limit as h approaches 0. Take a look at what happens up here. Those x squareds cancel out. Now the terms that I have left in the numerator have h in both of them, and I can pull that h out. So I'd be left with 2x plus h, and that's over h. Now these h's cancel out. So we're left with the limit as h approaches 0 of 2x plus h. And now I can put that 0 in for h. Right there, that becomes 2x plus, so I got rid of the limit because I'm actually putting that 0 in. 2x plus 0 is just 2x. So that is the derivative function. F prime of x is 2x. So how does that derivative function help us? Well, now that we have the derivative function, we can find the derivative at any value of this original function. Okay, so if I gave you a value, instead of going through the whole process and just finding the slope at that value, we can use this and find the slope at any value by quickly just plugging that value in. So I'll give you an example. Find f prime of 3 now using that same function where f was x squared. That would just mean you put 3 in, we get 6. So what we just said is the derivative of this function at 3 is 6. Well, look back at example, I think, what is it? Example 3. Right there. Example 3a. Look at same function. What is the instantaneous velocity of the ball after 3 seconds? Look what we got. 6. So we got the same thing here by finding the derivative. Where is it at? wrong page, by finding the derivative function and then putting 3 into our derivative function, and we got that value 6. But now the nice thing is we can find the derivative at any value. F prime of 15, for example, would be 30. So at 15 seconds, the ball is traveling at 30 feet per second. So we can find values more quickly. We have the entire derivative function there. All right. Last example here, we're going to find the derivative of y with respect to x of y equals 1 over x. So we're going to find the derivative of that function right there. So limit. Actually, let's start with this. The derivative of y with respect to x here is going to be equal to the limit as h approaches 0 of, we'll use our limit definition here of a derivative as h approaches 0. We've got, let's see, f of x plus h minus f of x. Okay, so again, I just rewrote the formula for no other reason but to establish what colors my expressions are going to equal here. So, okay, check this out. F of x plus h now is 1 over x plus h. You're just putting x plus h in for x right there. So there it is. Obviously, f of x, or y, is 1 over x. That's given to us. So we have f of x plus h at 1 over x plus h minus 1 over x. So what we want to do here is combine these two fractions in that numerator there, combine those two expressions up there. So we're going to have to get a common denominator. Okay, so our common denominator would be the product of those two denominators. We'd have to multiply this guy by x plus h over x plus h. We have to multiply this guy by x over x. Okay, if you want to call it, put it in as a fraction, you can. So what I would get then is 1. Actually, I'm going to change this here real quick. Instead of dividing by h, I'm going to multiply by 1 over h. So this idea of dividing by h, I just switched to this. Okay, so now what I have here is this fraction here becomes x over x times x plus h, and this guy becomes x plus h, just times 1 is itself, times x plus h. And then instead of putting it over h, I'm just multiplying it by 1 over h right there. All right, now we can combine these two into one fraction. When we do that, when we combine these into one fraction, huge thing to remember here. Really, really, really important. So first of all, when I add these together, red plus blue equals purple. But here's the big thing. We have x, and then we have minus x plus h. But remember, this needs to be distributed to this. Okay? Both of those are being subtracted. So you either need to use parentheses and write one more step, or know that this is going to become minus x minus h. And our denominator is now that LCD that we got in both of them. Okay? This is being multiplied by 1 over h yet. Now notice how we can't yet put 0 in for h because it would put a 0 in that denominator right there. But look what happens here. This x and this x are going to cancel out, and we are left with the limit as h approaches 0 of negative h over x times x plus h, and that is being multiplied by 1 over h, and these h's right here cancel out, which means which means I can now put 0 in for h. Because if you look at what this becomes, just write our simplified form here. I'm going to multiply them together. So I'd have -1, put the -1 in front, -1 over x times x plus h, after those h's cancel out. If you put in 0 for h and let that become 0, it doesn't make your denominator 0. Our denominator is going to become x times x. So our new function, our derivative function, is -1 over x squared. The derivative of y with respect to x is -1 over x squared. There's our derivative function. All right, that's it for 11.1. You need some practice here, so get to that homework. If you got questions, let me know.